Welcome back to section 4.6. Let's finish up with some geometry and the invertible matrix theorem. So the new parts to our invertible matrix theorem are these last four. If A is invertible, then call A is all of Rn. In that case, if call A is all of Rn, then the dimension of call A is n. So, whoops, sorry about that. So O and Q go together. The rank is n, meaning the dimension. The rank is the dimension of the space. So O is a statement about the vector space, and Q is a statement about the dimension. Now, if the rank is n, and the rank plus the nullity has to equal n, that means the nullity is 0. If the nullity is 0, that means null A is the 0 vector space. So P and R also go together. All right, let's look at the 6 fundamental vector spaces if we have A is an M by N matrix. So if we consider A and A transpose, A maps Rn to Rm, and A transpose maps Rm to Rn. That's a little n. So although there are actually six vector spaces, only 4 are unique. Rho A is the same as call A transpose, and call A is the same as rho A transpose. So that leaves us with 4 vector spaces, and we want to figure out where they live. So if A maps Rn to Rm, null A lives over here. Null A lives over here. Call A lives over here. We've already seen that. A transpose goes from Rm to Rn, so null A transpose has to live over here. And then what's missing is rho A. Rho A lives over here. So in each space, I've got 2 subspaces, and the fascinating thing that we'll learn in chapter 6 is these subspaces live in Rn in a very special way. They have 0 intersection. Same with these 2 subspaces here. And I'll give you a preview of that with an example. So let's make it concrete. A is a 2 by 3 matrix. So A maps R3 to R2. So null A and rho A, they live in R3. Let's find a basis for each one. A basis for null A, in order to do that, we need to take the reduced form of A, augment with the 0 vector. So we get 3 variables. X3 is T, X2 is S, and X1 is T. So the basis for null A would be 1, 0, 1, and 0, 1, 0. So that's going to form a plane in R3 because it's spanned by 2 vectors that are not multiples of one another. Basis for rho A, we take the non-zero rows of B. I'm going to put this one in as a column. So I'm looking at this row, but I'm going to put it in as a column. 1, 0, negative 1. That's a line in R3. And notice that if you dot any vector in rho A with any vector in null A, you'll get the 0 vector. So they live orthogonally. And so we'll discuss that more when we get to chapter 6 and we have the right vocabulary. But this line is actually perpendicular to this plane. Okay, call A and null A transpose These guys live over in R2. All right, so A maps R3 to R2, null A and row A live in the domain, and then col A and null A transpose live in the codomain, which is R2. So a basis for col A, we look at the pivot columns of B, there's only one pivot column of B, and we use the corresponding column from A, 1, 2. Basis for null A transpose, well, I have the reduced A transpose up there. If I augment that with the 0 vector, I get two variables, x2 is t and x1 is negative 2t. So a basis for null A would be negative 2, 1. So col A is a line in R2, and so is null A transpose. And those two lines are actually perpendicular. If you look at the dot product between 1, 2 and negative 2, 1, you get 0. But again, that's a preview of what's to come. So that does it for this section.